So let's start. We started moving towards the Gauss's law in the previous lecture, one of the fundamental laws in physics and, of course, in the course of electricity and magnetism. All right, and one of the crucial components in the Gauss's law is the electric flux. So we cannot introduce Gauss's law without properly discussing the idea of the electric flux. So today we're going to do that. I will just first review the major points, major ideas about the electric flux, and then we will solve 2-3 problems. Right? And it should be enough. It's not that complicated. So first, probably let's introduce the area vector. It's just basically a very artificial mathematical idea. Don't try to find any meaning behind this area vector. There's not much, right? It's just a vector which allows us to make expressions, some formulas, look much more compact, much more elegant, right? So the idea is very simple behind this area vector. So if you have a surface, any surface, all right, so the area vector by definition, all the time perpendicular to the surface, right? So perpendicular to the surface, and the magnitude of this vector, area vector, equals to the area of this surface. As simple as that. So let me write that down, and of course from now on we will be using this area vector, okay, from time to time. So the area vector, okay, I drew this picture. And so the area vector, by definition, is perpendicular, right? So if you have a surface like this, of course, you have a freedom. You can choose the direction up or down. Right now, there are no any restrictions. At some point, there will be some additional restrictions, but I will tell you at that moment. So first part, of course, this vector, area vector, is perpendicular to the surface. So it's a first part of the description of the area vector. And second, as I said, second part, absolute value, which we have wrote it. Okay. So absolute value of this area vector equals to the area. Okay. So by definition, again, as I said, don't try to find any meaning. Just need to get used to that, right? Because it's very useful. So it's a first bullet. And now let's introduce actually the electric flux for the simplest possible case. When you have, for example, a flat surface, all right? So if you have a flat surface, and let's say this surface is exposed to some electric field. Of course, you can draw a bunch of electric field lines. So of course, some of those electric field lines are going to cross this surface. So basically, the electric flux allows us to count, right, number of electric field lines crossing a certain surface. So that's the physical meaning of the electric flux. It's a number of electric field lines crossing this or that surface. Right. And very similar idea will be in a couple of months when we will introduce the magnetic flux. But here we're dealing still with the electric flux, right? Okay, so the simplest situation, flat surface, uniform magnetic field. Right. All right. So electric flux now. Okay, I'll have to rewrite it again, electric flux. And so let's assume that we have flat surface and uniform electric case, or I mean the electric field, uniform electric field. Maybe I can even draw some diagram, for example, let's say over here. So I can draw electric field lines. So this is E, right? And surface, which way I should draw, maybe like this. Right, so let's say this is my flat surface. All right, it's slightly tilted. Okay, maybe it's not the best picture, but I tried to do my best. So now let me also draw on this diagram this area vector which we just introduced. Right, so let's say it points this way. So let's say this is area vector A. Right. Okay, so now we can write expression for the electric flux for this simplest case. Right, so we can write flux, electric flux equals a dot or scalar product between electric field and the area vector. You remember from physics 1, scalar product. Okay, here at the end, after I review these ideas of flux, I will write again formulas which can be used to calculate the dot product or scalar product. But I'm sure that you remember from physics 1. Okay, let me frame this. Mainly, we're going to use today that expression. So that's the simplest situation for the electric flux, when we have a flat surface and uniform electric field. Now let's make the situation more complicated. Let me check if I mention everything. Yeah. Okay, so now next one, what if we have, which way I wrote? Okay, if A is not flat. Yeah. What if surface is not flat, and non-uniform electric field. Electric field is not uniform. So that's, of course, a more general situation, and of course more complicated. In this case, how can we calculate flux? Let me assume that we have a maybe a surface like this. Right. It's basically any surface, you just curved it, right, in any way. Well, I drew it this way. And so in order to calculate flux, and of course it's exposed to some electric field. Of course, I will draw in a second a few electric field lines. But for now, let's say this is my surface. And so in order to calculate the total flux, what do I have to do? I need to slice this surface into small sections. So it will be something like, which way I drew it? Oh, something like this, right? Right. So I slice it into small sections. And now I have to take a small patch with some small area dA, and I can draw my area vector. Let me use blue. Right. So let's say this is area vector for that patch dA, and of course there will be at this at the place of this patch there will be of course some electric field, the value of the electric field at this particular point. So let's say this is E, right? So now we can write the flux through this small patch as E dot dA, like over here. Tomorrow I will just spend a few minutes on this because we didn't manage to get to this point. So flux through this small patch will be E dot dA. But then, since we're interested in the flux through the whole surface, we just need to integrate this expression. Again, what does it mean, integration? Integration is just a fancy word for adding small contributions. So small contribution from this patch, then plus small contribution from that patch, plus from that, plus, and you keep moving, keep adding until you cover the whole surface. That's what integration is, right? So if I put here integral, it just means that I added all these small contributions to the total electric flux, right? Okay, so now I can write here, so it's a flux in this case can be found using this expression. This expression is more general. This is the special case of this situation. Right? So let me frame this. And enough about the flux. And now the last piece, let's recall. how we can calculate the dot product or scalar product, right? Because again, you discussed it in Physics 1, but still many students forget about it. Because if you don't use something on a regular basis, it's a natural ability of our, and naturally for us to forget it. Right? Okay, so I will put a new bullet and let me write, so let's refresh scalar, or sometimes it's called a dot product. Right. So what is that? So if you, let's say, have two vectors. Let me draw vector A. I use small a, yeah. And let's say vector B, right? So we can calculate a scalar or dot product of these two vectors, right? So it can be done either, let me write it here. Yeah, I should be able to squeeze A dot B. So if you know absolute value of this vector and absolute value of that vector, it's better to use this A times B times cosine of angle between these two vectors, the correct angle between these two vectors. How can we find the correct angle? You need to take both vectors and position their tails at the same point. For example, like this or like this, it depends on the orientation, right? But their tails must be at the same point. And this will be the correct angle. These rules students tend to forget, right? If you position vectors like this, it's not correct. This is not the correct angle. Right? But you remember what you can do with any vector. If you grab it, and if you preserve its magnitude and direction, you can move it anywhere you want. Again, unless, or only if you preserve its magnitude, length, and direction, but you can move it anywhere you want. So if you, for example, have this situation, these two vectors, and you want to find a dot product, you can just grab this and move it over here, right? Now their tails are at the same point, and you can find the correct angle between these two vectors. Okay, so now in our picture, this is the correct angle, right? Because their tails are at the same point, and the angle less than 180 degrees is the correct one. So if magnitudes are given, you can use this formula. It's one way of calculating the scalar product. Maybe I can put 1, right? Now, the second one, if these vectors are written in the component form, then you can calculate dot product in this way. A dot B. It just, you multiply the corresponding components. For example, first X components, then Y components, multiply, then Z components, and then add up all those products. So basically you'll have AX, BX plus A sub Y, B sub Y plus A sub Z, B sub Z. So there are two ways of calculating the dot or scalar product. Right? Again, this is easier when vectors are written in the component form, and if magnitudes are given, the first one is easier. But of course, it doesn't matter if you use this formula or that formula, the answer will be exactly the same. Right? The number will be exactly the same if you use any of these options. Okay, so that's what we need for today. And now, if you don't have any questions, but if you do, of course, you can ask immediately, right? Then let's look at a couple of problems. Actually, I'm planning to discuss 3. Yep, this we discussed. Okay, so first, it's a chapter 24, problem number 10. So I'll move to this side, 24.10. And so what we have? We have a surface and the electric field. Maybe I will start with drawing a surface. Yeah, I will draw the surface first. Let's say right. Okay, then sides. This is A 10 centimeters. B also 10 centimeters. Okay, B also 10 centimeters. right? So that's the surface, and in this case, it's flat. And we have information about the electric field. So we have, let me write, so we have flat surface, A by B, right? And then we have information about the electric field strength. You see, I put an absolute value, basically magnitude, the strength of the electric field. And that is 200 units. Again, you remember there's no special unit for the electric field, just whatever you see in the formula which we introduced to find electric field, force divided by charge. So it's a newtons divided by coulombs. Right. Newtons divided by coulombs. And all right, so also we have some information about the direction of this electric field. Okay, let me draw a few vectors over here. So let's say, all right, something like this. So let's say this is my electric field, and one angle is given. If I draw this dashed line, which belongs to this surface, you see dashed line. Maybe I need to make it a little bit, okay, solid. So this angle is given. Let's call it phi, and it's 30 degrees. So angle phi. Okay, so that's what is given in the problem. And of course, the question is find the electric flux. So we have a surface, we have electric field. Of course, we can count number of electric field lines crossing that surface. Again, that's the physical meaning of the electric flux. Number of electric field lines crossing a surface. So the question is, of course, we need to find phi, Greek letter phi with the subscript E. Because when we move to the magnetism, there will be magnetic flux, and here we will write letter B or M, right? Telling that will be a magnetic flux, but here electric flux, right? Okay, so now it's a case of a flat surface, uniform electric field, right? Because direction is the same everywhere, right? Direction of the electric field, and the strength is the same, uniform electric field. So we can just grab this and start applying. So ideologically, pretty much not much physics that we can discuss here. It's just we introduce a new quantity and we need to practice it to get used to that. So flux, of course, can be found by taking a dot product between the electric field and the area vector. Okay, quick question for you, right? But usually I don't wait for your answers because now it's more difficult to communicate. But when I have normal classes, of course, all these question goes to somebody, right? And I'm trying to get answers from students. So, which formula is better to use to calculate electric flux in this case, right? So the first one or the second one? But of course, more or less obvious for everyone, right? So the first one will be the best, the easiest one. Of course, you can still get you can still use this, but of course, first you will have to spend some time finding these components, which is possible, but will be complicated, right? More complicated than if you use the first formula. The first formula is the best for this situation, right? Okay. So we can write the flux now explicitly, so it will be E times A n times cosine of angle. And now I would usually pose, okay, yeah, of course it should be, okay, we have here theta, right? So what, no, maybe I'm not going to write anything. Which angle should we use over there? Think for a second, right? In order sort of to have a decision, which angle. And again, during the normal semester, right, I usually try to get information that answers from students and Still, plenty of students just grab this angle phi and start using over here. But it's not the correct angle. Why it's not the correct angle? In order to see that, let's also draw area vector in the picture. Because without that vector, it's more difficult to see which angle is the correct one. So let me draw area vector first. All right, so probably I will use blue. So area vector must be perpendicular, so it will go just straight up. Right, so this will be my area vector A. Right? And now we need to recall this. How can we find the correct angle between two vectors? Their tails must be at the same point. Again, you can grab one of the vectors and move it so that their tails be at the same point, but in our case, tails are already at the same point of both vectors. You see, tails of A and tails of E are at the same point. So that's the correct configuration, and as a result, which is the correct angle? It's this one. You see with those two lines. That's the correct angle that must be used in this formula. The angle which is given phi, it's not the correct one to use. Right? I will keep bugging you guys about how to find the correct angle throughout the whole semester. Okay? So, theta. And of course, let me open my explanation box and show how we can find that correct angle theta. So, theta and phi, they complement each other to 90 degrees. So, theta will be 60 degrees, right? So, theta will be 90 degrees minus phi, so which is 60 degrees. So, that's what we should use, right? So then, area vector, don't use centimeters, use meters, right? So we can write electric field, and then area A times B times cosine of theta. Right? Okay, now let me plug numbers in this case to emphasize that use meters, not centimeters. So it will be, it's a 200. All right, 200 newtons per coulomb times 0.1 meters times 0.1 meters times cosine of 60 degrees. Again, I emphasize meters. Right. Okay, so cosine of 60 degrees, it's 1 over 2. Cosine of 60 degrees equals to sine of 30 degrees, so it's 1 over 2. Here it's 1 over 10, 1 over 10, so it's 1 over 100. So this 100 and that 100 gets cancelled. Here we have 2, here 1 over 2. Again, 2 gets cancelled, and we'll have only 1. No special units for the electric flux, just whatever you see in the formula. Newtons divided by coulombs times meters to the power of 2. Right? So you will end up, okay, let me check if I got the right, number is correct. 1 newtons times meters squared divided by coulombs. So this is, again, electric flux. It's a tool which allows us to calculate number of electric field lines crossing this, okay, in this case, this particular surface. It's a very simple idea, reasonably simple. You just need to get used, and then usually students don't struggle with that. Okay, so now, again, if something is not clear, if something confuses you, tell me immediately. I can easily clarify. Okay, I hope I can easily clarify it. Right. Okay, so if you don't have, then I will start moving to the next one, the next problem. Okay, if you're not asking that, okay, I will start erasing because I doubt that this space will be enough. Okay. Okay, right. So I can erase this. Erase everything. I will erase everything. So 12.8. And again, similar problems will be in your homework. Very, very similar. So 12A. So there's also part B, but we're going to solve only part A. I think in homework will be part A and B. So what do we have in this case? Again, flat surface and the field. I will ask the question about the field in a second. So you know what? In this problem, let me start with drawing a coordinate system first, because we know that the surface lies in the xy plane. Okay, so in order to draw it properly, we need to introduce coordinate system immediately, right? Okay, so let me do that. So let's say this is z. This is, okay, it's slightly not straight. So y and x. So right-handed coordinate system. And our surface lies in the xy plane. So in this surface, in this plane, our surface is in this plane. Okay, I will use black. All right, so AB. Right. So that's my surface. Maybe I slightly highlight it like this, with the very light lines. And of course, we know that this side is a 2 centimeters, and this side B 3 centimeters. Then, so we have plenty of information about the surface. Now we need information about the electric field in order, again, to calculate the electric flux. Information about the electric field is this. All right, so let's say E equals, so it's 100 times I hat. You remember I had unit vector showing positive direction of the x-axis. Then minus 200k, k hat. And of course units, newtons per coulombs. Again, k hat, now it's a unit vector in the positive z direction. Right. So that's what is given, right? And again, the same question. Find the electric flux. Flat surface. Now, okay, let me ask you, but again, I cannot demand an answer from you, but what can you say about this electric field? Is it uniform? Again, I'm asking you because based on my experience, when we have normal, real human interactions, right, not progressive interactions through the screens of the computer, right, some students are not very comfortable when I ask them, is this a uniform magnetic field? And they hesitate. They are not comfortable because it looks kind of complicated. It's not just one number. No, it's still uniform. This complicated form that it has x component and z component tells us just it has some reasonably complicated direction, right? But direction will be exactly the same at any point, and magnitude is still the same. So it is still a uniform electric field, right? Again, so if you were hesitating, if you are not comfortable to say, so yes, it's a uniform electric field, it is. It's still a uniform electric field. So we have flat surface, uniform electric field, so we can still use this expression, the simplest one, to calculate the electric flux. Okay? Let me also emphasize, so it's still uniform. Still uniform electric field, right? It's still uniform electric field, just so that you will have it, in your notes. All right, okay, so now this is the expression, of course. Let me rewrite it because we sort of justified that we can use that. And now, of course, the next question, dot product, scalar product, which formula should be better to use, this or that? And I think again, it's more or less obvious. Of course, you can use even this. It will just take a little bit of more time to find all these ingredients to calculate the dot product using the first formula. In this case, in this particular case, of course, it's better to use the second one. On purpose, I picked these two problems so that we can practice both formulas to calculate the dot product. First this, and now that. Basically, one of the ideas of these problems to refresh how to deal with scalar product. Right? Because again, by this point, usually students forget about this. So this is the best one. Right? So I will just write down then explicitly, so it will be EX, which way I wrote A, just AX, right, you see, multiplying X components, then plus product of Y components, plus product of Z components. And now, obviously, we have EX, EY, AZ, all right, they're given. But we need to write down AX, AY, and AZ. Now we need to write components of the area vector. Okay, now we need to write this, right, in a component form. And again, based on my experience, so when I ask students, right, can you write components of the electric field, right? And lots of students not comfortable and start panicking, right? And they cannot answer, right? But once I ask them, can you draw area vector on a diagram? Okay, and you remember area vector must be perpendicular to the surface. Of course, you have a freedom. You can pick area vector either up or crashing my system, right? Either up or down. Okay, let me pick up. All right. Again, you have a freedom. You can pick any direction, right? So let me pick it this way. So that's my area vector. Okay, I use different color usually for the area vector, but why not? Right. And now if I ask the student, right, so can you write components of this vector? Of course, now they start realizing, yeah, of course, so the X component will be 0, right? Y component will be 0 because direction perpendicular to the surface, which lies in the XY plane, direction of A is along Z, right? The surface is in the XY plane, perpendicular direction is the Z direction. So X component of the area vector must be 0, Y component must be 0, and the whole magnitude is in the Z direction, right? So now we can easily write down components. So diagrams are very important, right? It simplifies, right? So now I can write, so it will be 0 times I hat, right? So you see 0 component in the X direction, plus 0 component in the Y direction. And Z direction, of course, it will be just A times B, K hat, right? You remember the absolute value equals to the area, absolute value of A. So that's why I wrote A times B, because that's the absolute value, the area of that surface, right? Okay, we can actually calculate this A times B, right? A times B, again, don't forget to convert to meters. So it will be 2 times 10 to the power of minus 2 meters times 3 times 10 to the power of minus 2 meters. And of course, in a K hat direction. So it will be 6 times 10 to the power of negative 4. 6 times 10 to the power of negative 4. And in the Z direction, K hat. Okay, so now we are ready. We can go back to this. And so now we have all A components of A vector, components of E vector. So now we're all set to finalize the problem. So now let's just take care of the total flux. Flux will be equal. So Ex 100. Okay, let me put it down. So E sub x 100. A sub x 0. Then plus E sub y. It's not there. You see there is no j. It means just y component of the electric field is 0. Right? So it's a 0 times A sub y. A sub y also 0. And then plus E sub z negative 200. And times A sub z. A sub z, we just calculated 6 times 10 to the power of negative 4. 6 times 10 to the power of negative 4 m squared. Right? Okay, so almost done. So now if you multiply that, you will end up with what? Oh my God, so it will be 12, 10 to the power of negative 2, so it will be 0.12 negative minus 1.12 newtons times meters to the power of 2 divided by coulombs. Of course, if you picked, for example, from the very beginning, area vector downward, your flux would be positive. So you have, in this case, freedom to choose direction. But of course, in the homework problem, it will ask you, because every semester it creates some confusion. Read carefully the problem. It will ask you what sort of the absolute value of the flux, or something like what's the magnitude of the flux. It just basically means that they don't care about the plus or minus, don't care about the minus, right? Because every semester students send me emails asking, so how come that mastering physics doesn't accept the answer? Just read the problem carefully, right? Because actually, first year, it was a mistake in mastering physics, maybe like 4 or 5 years ago. And then I wrote them email, guys, no, you cannot, you have to change the wording of the problem because you confuse us, because you can pick area vector either up or down. As a result, they rephrase the problem, the question. So they started asking for absolute value. All right. Giving you a universal freedom to choose direction of A, either up or down. Okay, so that's the second one. And again, the goal was to practice this and that dot product. All right, so what's the time? Okay, we still have 12 minutes. Good. Okay, if something, again, still confuses you, go ahead, ask. Also, today from 2 to 3, there will be office hours. You can come and ask questions. I will be just streaming, and whenever you're ready, you can come. Just start saying, and I will come over. Right, okay, so if you don't have questions, let me start erasing this, and let's look at slightly more complicated problem. Okay, since I'm not... Okay, awesome, I can see your thumb. All right, so then let me erase it. And now, surface will be more complicated. So let's assume that we have a cylinder. Before the class, I was walking around trying to find some cylinder more looking more elegant, but I couldn't find anything better than a jar with apricot preserve. So now let's assume that we have a surface like this, cylinder. So which has consists of 3 parts, basically: cylindrical wall, front facet, and back facet. So, and of course, let's assume that it will be exposed to some uniform electric field. We have to find the net flux through this surface, cylindrical surface, right? Okay, so let me draw the picture, and this is problem 16a. Very similar will be in your homework. Right. Okay, let me again draw the picture. Uniform electric field. All right, I will probably draw it here. Yeah. Right. It should be enough, 3 lines. Right. Then cylinder. Let me draw it here. Okay, so cylindrical surface exposed to a uniform electric field. So what do we know about the... okay, numbers are not given. All right, so we're going to just use E. Right, so let's assume that electric field of strength E. There are no numbers. And so, yeah, we need to find flux. Find, again, electric flux. So, I hate these talking speakers, right? Sometimes in the middle of the night, low battery, right, with this low voice, right, almost scaring you. Ingenious, right? All right. Yes. So what should be the first step, all right, in the problem? First of all, we need to split this surface into 3 surfaces, obviously, right? Because it's a complicated structure. So we have 3 parts. Front facet. We can easily find the flux like we just did many times, right? Oh, twice. Then this back facet. Again, it's a flat surface. We should be able to find flux. And also we have this cylindrical wall. Of course, now it's a cylindrical wall, it's not flat. So we will have to use that expression. So we'll have to calculate 3 fluxes. In the Gauss's law, we're going to do this many times, right? Okay, so that's why I picked this problem, sort of to prepare you emotionally, right, physically, for the Gauss's law problems, right? Okay, so maybe underneath I will write, so we need to split the surface into 3 parts. Okay, let me label them on the diagram. Yeah, it's important, right? I'll probably use black. Oh, yeah, let me use black. So this surface, let me label it as S1. So this cylindrical wall. You see this cylindrical wall. Then this, let me label it as S2, front facet or front side. And the back side, S3. Right, so S3. So S1, S2, S3. All right. And so as a result, flux is additive thing. So we just, net flux will be flux through the first surface plus flux through the second, and so on. So this total flux will be flux through S1 plus flux through S2 plus flux through S3. Okay? And yeah, let's start with more complicated flux expression. Let's find the flux through that cylindrical wall. All right, flux through this surface, cylindrical wall. Okay, let me write underneath. So, okay, you know what? I'll give you a chance. Maybe somebody can tell me immediately what will be the answer for the flux through that surface S1. And then I will show, of course, mathematically. Conceptually, can you see what will be the value of that flux?
I want to say 0.
0. What did you say?
I said 0, but I'm not sure.
0. Why not sure? Come on, you should be really, really confident. Why? Because you remember the physical meaning of the electric flux. It's a number of electric field lines crossing the surface. But in our case, electric field lines, you see, they are parallel to this cylindrical wall. So they physically cannot cross that cylindrical wall, right? So, of course, the flux will be 0. But again, it's a conceptual approach, right, to justify. But of course, we should be able to do it mathematically using this formula, right? But of course, you're absolutely right, because electric field lines are parallel to that cylindrical wall. Parallel, it means they're not physically crossing it. Right. Okay, but anyway, so it's not flat, so I have to use an integral E dot dA. And I emphasize, so S1 not flat, not flat. So that's why I have to use that integral. And of course, strictly speaking, it's a calculus 3. This integration is not trivial, but you will see in a second that we can easily calculate it, although integral is not trivial. So let's write explicitly. It's a dot product. A dot product, let's use this. E dA times cosine of angle, right? So it's integral E dA times cosine of angle. And now I will pose which angle. Pose in order to sort of discuss the angle. So in order to see what's the value of the angle, let me draw this area vector dA. Of course, I can take this small patch, for example. That's the small patch of the surface, cylindrical surface. And the area vector perpendicular. Okay, I'm trying to draw three-dimensional situation. So that's dA. Okay, let me use my jar again. So here the jar, right? So electric field that way, right? But the area vector perpendicular to the surface, right? So what's the angle between this area vector and the direction of the electric field?
So 90 degrees.
90 degrees. And cosine of 90 degrees is
0.
0. That's the mathematical explanation of the zero flux. Cosine of 90 degrees. And of course, cosine of 90 degrees is 0. So the whole integral is 0. So that's how we can get it mathematically. But conceptually, we already discussed. Okay, so that's the tricky part. And now flux through the second surface, S2. Of course, that's the flat one. So we can use this. E dot A. All right. And of course, what's the direction of the area vector for this surface, front facet? Area vector, you see, perpendicular. Yeah, it's S2. It's this one. It's so it points that way. Area vector, right? You see, but the electric field that way. You see, electric field points this way, but this vector S2 that way. Another thing which I should have mentioned, when we have the surfaces like this, sort of closed, tomorrow I will mention it one more time in the lecture, area vector must be pointing outward. I will tell about that tomorrow in the lecture. Right? So area vector in this case is for this, that way. Okay, I will write outward. Right. So as a result, I can write this as EA and cosine. What's the angle between the vector pointing this way and vector E pointing that way?
180.
180 degrees, or pi. 180 degrees, which is equal to -1. So we're getting the flux minus EA. So that's the value of the flux. Numbers are not given. You will see in a second why numbers are not given. So now let's do the same for S3. Again, S3, it's that, again, flat, so we can use E dot A. And the same thing, let me draw the area vector. Again, it must point outward. So that's A, again, outward. So now, direction of E that way, direction of A also that way. So the angle between them, 0. So EA times cosine of 0 degrees. And cosine of 0 degrees, of course, is 1. So this equals to 1. So as a result, the flux EA Okay, so class is over, and as a result, now we can plug these results over here, right? And as a result, we're getting a nice number. So it will be flux through this S1, it's 0. Flux through the S2 minus EA. And flux through S3 plus E times A. The answer is 0. So that's why numbers were not given in the problem, because anyway, it doesn't matter what's the area, what's the value of the electric field. Fluxes through this surface and flux through that surface, they cancel each other, giving us 0. Right. It just means that number of electric field lines entering the surface, entering the cylinder, and leaving are exactly the same. But of course, as a result, one is flux is positive, the other flux is negative. Okay, so very similar will be in your homework. Now you got the idea. Okay, guys, so let's call it a day. If you have questions, we can spend a few minutes.